you've probably already seen matrices in different forms, but not known that they were matrices. Basically, a matrix is just any rectangular array of numbers which are in rows and columns. So any type of table that you've ever seen, maybe, or here they've got an example of the A-League table. This could be rearranged in such a way that we make it a matrix. So basically, the numbers within this table are the important bit which would be used in the matrix. So you can see down here, they've converted this shopping list, which is you would commonly call a table, into a matrix. So basically, they've just taken the numbers and put them into a column. And this thing here is what we call a matrix. So here we've got another one. They've got some furniture inventory, and we can see depending on what are they showing, there's a flat, a unit, a house, and then they're saying in this flat there's 6 chairs, 1 table, 2 beds. In this unit there's 9 chairs, 2 tables, 3 beds. In the house there's 10 chairs, 3 tables, 4 beds. So this information here is transferred into a matrix over here, and you can see the F, the U, the H just stands for flat, unit, house. The C, T, B stands for chairs, tables, beds. But generally when we use matrices, we end up dropping those letters, and you often see the matrix like this. Where's this important? When we start looking at things like computer programming, you can use matrices to store a lot of information, and you'll see there's actually quite a few different applications for it. So I'm just going to watch a quick Khan Academy video because he gives...
What I want to do in this video is explore the notion of a matrix outside of the context of a surprisingly good movie that involves Keanu Reeves, and it's actually the first of 3. I guess we could call the 3 movies combined the Matrices. And there is a relationship between the movie, which is about a virtual reality constructed by super smart computers, and the relation and the notion of what a matrix is when you study it in mathematics or when you study it in computer science. And the connection really is that matrices are used a lot when you are simulating things or when you're constructing things in computer science, especially in, frankly, computer graphics. So the super intelligent robots that made the Matrix in the movie Matrix were probably using matrices in order to do it, if they actually did exist. Now, what is a matrix then? Well, that's a fairly simple answer. It's just a rectangular array of numbers. So, for example, this right over here, I have 1, 0, -7, pi, 5, and, I don't know, 11. This is a matrix. This is a matrix where 1, 0, -7, pi, each of those are an entry in the matrix. This matrix right over here has 2 rows, and it has three columns. And because it has 2 rows and 3 columns, people will often say that this is a 2 by 3 matrix. Whenever they say it's a something by something matrix, they're telling you that it has 2 rows. So you see the 2 rows right over there, and they're telling you that it has 3 columns. You see the 3 columns right over there. I could give you other examples of a matrix. So I could have a 1 by 1 matrix. So I could have the matrix 1. This right over here is a 1 by 1 matrix. It has 1 row, 1 column. I could have a matrix like this: 3, 7, and 17.
Would you know how to describe that one? Is it a 1 by 3 or a 3 by 1?
3 by 1. 1 by 3.
1 by 3.
Yeah, you always say the rows first. All right, so this would be a 1 by 3.
What is this? Well, this has 1 row. This is the 1 row we see here, and it has 3 columns. This is a 1 by 3 matrix. I could have a matrix, and I think you see where all of this is going. Figuring out the dimensions of a matrix are not too difficult. I could have a matrix that looks like this, where it's 3, 5, 0, 0, -1, -7. This 7, -7. This right over here has 3 rows. So it's 3 rows, and it has two columns. So we would call this a 3 by 2. Oh, let me do that in that same color. We would call it a 3 by 2 matrix. 3 rows and 2 columns. So fair enough. You know that a matrix is just a rectangular array of numbers. You can say what its dimensions are. You know that each of these numbers that take one of these positions, we just call those entries. But what are matrices good for? I still might not be clear what the connection is between this and this right over here. And at the most fundamental level, these are just ways, this is just a compact representation of a bunch of numbers. It's a way of representing information. They become very valuable in computer graphics because these numbers could represent the color intensity at a certain point. They could represent whether an object is there at a certain point. And as we develop an algebra around matrices, and when we talk about developing an algebra around matrices, we're going to talk about operations that we're going to perform on matrices that we would normally perform with numbers. So we're going to learn how, or we're going to essentially define how to multiply matrices, how to add matrices, how to we'll learn about taking an inverse of a matrix. And by coming up with an algebra of how we manipulate these things, it'll become very useful in the future when you're trying to write a computer graphics program or you're trying to do an economic simulation or a probability simulation to say, oh, I have this matrix that represents where different particles are in space, or I have this matrix that represents the state of some type of a game. And I know the algebra of matrices, and I know ways of doing it very efficiently so that I can multiply a bunch of them, or I could run a simulation and I can actually come up with useful results.
So like I said, computer science is one really good example of where a matrix will become important. All a matrix does is it stores information about different things. Like you said, it might be storing what the color of certain pixels are in your computer screen, or if you're playing a computer game, different information can be stored in that matrix to tell the console what to do. So one important thing that he touched on was how to describe what the matrices are. So in this situation here, we've got 4 rows, 1 column. So we call this a 4 by 1 matrix. You always say the rows first and then column second. This one here, we've got a 3 by 3 matrix, and if you want to describe a position of any of the numbers within the matrix, like this here, they've got this 3, we can say that that's in the 3rd row, 2nd column. Here, this is an example of a 1 times 4 matrix. So again, row first, column second. So if we see the terminology m times n used, that's just a way of more generally saying how big a matrix is. So you might have so m times n specifies the order of the matrix. So we could say it's a 3 by 2 matrix. You know, it's got 3 rows, 2 columns. Or it's a 2 by 2 matrix. It's got 2 rows, 2 columns. So that's just a general way of describing a matrix size. All right, so we'll just go through this example of them putting some information into a matrix. So Lisa goes shopping at store A to buy 2 loaves of bread at $2.65 each, 3 litres of milk at $1.55 per litre, and 500-gram tub of butter at $2.35. Represent the quantities purchased in a row matrix Q and the cost in a column matrix A. So we're doing 2 things. We're representing the quantities in one matrix, which is a row, and the costs in another matrix A, and that one is a column matrix. So one's going to be this way, one's going to be this way. So since she wants the quantities in a row matrix, we see that the quantities here, she bought 3 things. She brought bread, milk, and butter. So see how this is a row, and she bought 2 loaves of bread. She brought 3 litres of milk, and she bought 1 tub of butter. So that's the quantity in that matrix. And then they also wanted the costs in a column matrix A. So you just need to keep the order consistent. See how the first input in this matrix was for the bread. So the first input in this matrix here is going to be the cost of the bread, which was $2.65. And then the second input was for the milk. Therefore, the second matrix entry here is going to be for the milk, the cost of the milk, and then same thing for the butter, the third one and the third one. So that is a row matrix. This is a column matrix. And notice how they've labeled it Q. So they wanted you to represent the quantity in a row matrix Q. You could call the matrix whatever you want. they've just called it Q. Can anyone guess what the Q is standing for in this situation?
Quantity.
Yeah, quantities. And then they've called the cost matrix A. Again, you could call the matrix whatever you want to call it. Part B. When Lisa goes to a different supermarket, store B, she finds that the prices of the same items are $2.20 for bread, $1.50 for milk, and $2.20 for butter. So now the costs have differed to the initial cost. Write the cost for both stores in a single cost matrix C. So this is just going to be a way to compare the costs of the items at the two shops. So they've called this matrix C. They've got the cost from this first shop in the first column, and then in the second column they've just put the cost of the second. Alright, so all we are using, this is a very basic introduction. We're just showing you that you can input information into a matrix to give a reader an understanding of potential costs or some type of data in a easy to see format. Alright, so that's all we'll do for now. We will look at the addition and subtraction of matrices tomorrow. Just today, we're going to go through a few examples where you guys are going to read some information and try and put them into these matrices. Alright, so just get your exercise books out. First off, question 1A. If we were to write the order of these following matrices, remember it's always row first, column second. So I might just go through this one with you actually. So this is exercise 14A. So the first thing we'll write is just the fact that an M times N matrix has M rows and N columns. So, and M times N matrix has M rows and N columns. So e.g., if we had a matrix that was 1, 4, 3, 7, if we wanted to write the order of that matrix, it would be a what by what type of matrix. Just look at how many rows and columns there are.
1 by 4.
Yeah. Alright, so the order is 1 times 4. The next one, that's EG1, EG2. If we had a matrix like this, 2, 7, the order of that matrix, again, rows always goes first, columns always goes second, so that's going to be a 2 by 1 matrix. Or if you had a 2, 7, 8, 4, 1, 4, 3, 7. This matrix here, the order would be column, rows first, column second. 4 tie 2. Right, so that's the first main thing that you guys need to remember, that you always say rows first, column second when you're describing the order of these matrices. And when they say order, they're talking about basically the size. In this one here, a grocery list consists of 2 loaves of bread, 1 kilogram of butter, 6 eggs, and 1 carton of cream. Each loaf of bread costs $1.95, each kilogram of butter costs $2.35, and each egg costs 45 cents, and a carton of cream costs $2.95. Construct a row matrix showing quantities, and then construct a column matrix showing the prices. So the row matrix is for the quantities, and the column matrix is for the price. Now, they didn't tell us what we should label the matrix, so we can label them any letter we want. Since we're doing one for quantities, what might be a good letter to use to describe that matrix? Q. All right, and it's going to be a row. Now, how many things did we have? We had bread, butter, eggs, and a carton of cream. So 4 things. 1, 2, 3, 4. So that means that it's 1 row and how many columns? 4. Alright, so this is 2A. So for the quantities, they wanted a row matrix. So we've got 2 loaves of bread. So that will be the first value. Now you don't put commas in between them when we're drawing matrices. The second is 1 kilogram of butter. So it's going to be a 1. And we had...
Wait, how can we put columns in the example then? Commas. No.
I didn't. Oh, sorry, I shouldn't have. Alright, so you don't need to have those commas there. Alright, next one.
If you did put them there, what did you get?
You wouldn't lose marks, but just get in the habit of not doing it. Alright, I shouldn't have put those commas there. Then we have 6 eggs and 1 carton of cream, so the next ones are going to be 6 and 1. Alright, we're getting the point of this. And then for part B, they want us to do the costs in a column matrix. So costs, I'd use C to describe that matrix. And so the cost of the bread was $1.95 per loaf. So therefore the first input is going to be $1.95. You don't put in the dollar sign, you just write $1.95. Alright, it's just an easy way to input data. Then the butter costs $2.35, so that's our second input. And the egg costs 45 cents, so 0.45. And finally, the cream costs $2.95, so that will be the last input, $2.95. And that's your cost matrix.
Wait, so why are we doing B vertically?
Because that's just what the question asked us. A said construct a row matrix, B said construct a column matrix. There's actually a reason why they're getting us to do that, because later on when we do multiplication of matrices, there's some stuff that we'll learn that that's relevant for. Alright, and then this part C says, what is the significance of 2 times $1.95 plus 1 times $2.35 and so on? Can we all see what that there is showing us? Does that make sense why they'd be going 2 times $1.95?
Because there's 2 loaves of bread.
Yeah, because there's 2 loaves of bread, they're just multiplying it by the cost. So when we, and then there's 1 kilogram of butter, and a kilogram of butter is $2.35, and then there's 6 eggs, and they cost that much. So that's what this multiplication, what these different multiplications are. So this here would tell us the total cost of all of those items if they bought all of them. Now, what relation does that have to a matrix? Because eventually when we learn to multiply matrices by each other, that type of thing comes out from this. So if you were to say, if you were to answer their question, what's the significance of it? Basically, the sum shows us the total cost of the items. Alright, we'll leave that there.